Yeah, so dear students, hello and welcome to the today's class. And this is MA415 Algebra, and this is lecture number 31. Yeah. So today we will discuss about polynomial rings and their properties and Gauss lemmas and many more important results. So let me. So we already have idea about these polynomial rings, and we have describe what is the sum and put out other thing, right? So let me just briefly tell. So we have R, the integral domain. This is the minimum thing which I require, and then this is my polynomial ring. Ring over R. So what does that mean? That means these are collection of polynomials whose coefficients are from R, right? So like you write down fx equal to say summation ai x power I, say I equal to 0 to n, and these ai's are element of R. Okay, this is we already discussed. Now let me just define few more things. So when you just take okay, so maybe yeah, so I'm assuming the R is integral domain throughout these lectures. Okay, then the simple observation, maybe the properties, I can just write down properties of this Rx. Okay, so you can check that if you multiply two polynomials fx and gx, and then you show that the degree of this new polynomial is nothing but the degree of fx plus degree of gx. Okay, similarly property number 2, you check what are the units. So this is one, there is no need to prove, so I am not giving a proof. Maybe you can check one more thing, that what are the units of Rx. So units of Rx are nothing but are just the unit of the underlying ring, the ring R. Okay, so what does that mean? That means you are inside Rx, you are not getting any such extra invertible element. So whatever inside R, those will be becoming the units there only. Okay, and this is a simple proof. So how to prove this kind of statement? So let fx belongs to Rx be a unit in Rx. Okay, then there exists your gx belongs to Rx such that what happens, such that this fx times gx equal to 1 identity. So identity polynomial is the 1. Okay, and this will force that both fx and gx are constant means, so see, remember one thing, so these are polynomial, right? So so if you write down a0 a1x plus a2x square b0 b1x, then if the product is 0 and R is integral domain, so it's also R is an integral domain, so the only possibility is that they are constant polynomial. Okay, constant polynomial. So what does that mean, constant polynomial? Polynomials, that is this kind of fx is some constant c1 and gx is some constant c2 with c1 and c2 equal to 1, so they are also units in R. Okay, and conversely, obviously, if something is a unit in R, that will be again a unit in fx as a constant polynomial, right? So this is if and only condition. Okay, now one more property, I can check that R is integral domain, right? That is given, so that implies Rx is also. So I can say if and only actually also integral domain. So what does that mean? Suppose you know that R is integral domain, then if Rx is integral domain, and conversely, if you know that Rx is integral domain for some ring R, then R also integral domain. And the proof is also not difficult. So let R be, so one, but this was obvious, so let Rx be an integral domain okay, then R is integral domain, right? This is trivially. What does that mean? Trivially, I mean to say that if something is, if R contains a z divisor, that will be again 0 in Rx, right? So this is trivially, right? Conversely, let R be an integral domain. I'm writing in short, but you should not write only ID, should write integral domain directly. I'm just trying to save some time. So if R be an integral domain, then what happened? Then we know that, and we need to prove that Rs is integral domain, right? So what we should do? So let start with let fx not equal to 0 and gx not equal to 0 belongs to Rx to be to non-zero polynomial in Rx. Okay, we need to show that Rx is also the product is also non-zero, right? But whenever I am saying a non-zero thing, I mean to say that so you can write down that fx equal to summation ai x power I equal to 0 to n, and you see that the leading coefficient that says that n is not equal to 0, so that is the meaning of the polynomial degree n, right? So this is called the leading coefficient of fx. Okay, Similarly, for gx also you can do the similar thing, and you can have some bi xi, say I equal to 0 to m, and this bm is not equal to 0, right? This is in coefficient, and thus anbm not equal to 0 as R is an integral domain. Right, and hence fx gx not equal to 0, right? Because this is the highest term inside the product, right? So that proves that Rx is an integral domain. So these proofs are simple, so you can easily find out this proof. Okay, maybe one more property before saying that. So like if you want to quotient out by ideal, then what happen? For example, suppose you have a ring, so suppose you have ideal, this is ideal of R, okay, and then if you want to quotient out by this ideal, okay, and then take the polynomial ring over this ideal, okay, so I should not write down this, so I should say that this, and then polynomial ring over this. Okay, so on the one hand you write down this thing, and the other hand you have this, and then you can quotient out by the corresponding ideal here. What is that? So this is Ix is the polynomials, collection of polynomials with coefficient in I. Okay, now you see that this forms ideal. This is obviously this is homework. This is an ideal in Rx. Okay, so do it, homework, simple homework. Okay, so on the one hand you have this kind of structure, and the other hand you have these kind of structures, and natural question is that do you have any relation on those things, and the answer is that yeah, they are isomorphic. So the theorem or whatever property that Rx mod Ix is isomorphic to whatever. Okay, so some people also write down this as ideal generated by I. So this is also notation. Sometimes people also use this. Okay, this is isomorphic to R mod I, then X. Okay, and proof is also not so difficult. We will use that first isomorphism thing of rings. So what do we do? So we define a map that phi from Rx to R mod I of X. Okay, what is the natural map? So natural map is that you send a polynomial fx to f bar of x. So what is f bar of x? So f bar of x, where f bar of x is what? This is so if fx equal to summation ai xi I equal to 1 0 to say n, the f bar of x is equal to ai bar. So bar means that they are element of R mod I. Okay, so and then xi I equal to 0 to n. So this ai bars are element of R mod I. Okay, so this is a natural map, and then you can easily check that this map is a ring homomorphism, and not only that, this is onto map also. Okay, so this map is a surjective ring homomorphism thus by first isomorphism theorem of ring, we have Rx mod kernel of phi is isomorphic to R mod I what this, right? Now the question is that what is the kernel of this map? Okay, so this is the question which is remaining. Now what is the kernel of this map? Kernel of phi is by definition all those fx belongs to Rx such that phi of fx is identity 0, right? 0 in that, so let me write down 0 bar, whatever, doesn't matter. Okay, what does that mean? That means that fx belongs to Rx such that, so this is f bar, right? F bar of x equal to 0, right? What does that mean? F bar of x is 0 in R mod I of this, right? So what does that mean? That means the coefficient of fx are divisible by I, right? They are inside I actually. So fx is inside ix, right? So this implies since the fx is inside ix. Okay, so you are getting that this is subset of ix, and conversely, and also conversely ix also subset of this. This is obvious. Okay, kernel of phi, right? So what does that mean? That means kernel of phi is ix, and bingo, then it solves our problem, right? So Rx mod this is actually isomorphic to R mod I of x. Okay, so these are natural things, and one also ask what about so these are all polynomial ring on one variable. So you can also define polynomial ring of multi-variable, for example. Okay, so this ends the proof. Now for polynomial with multi-variable, what you can do, you can also, like, you can write down, say, R x1 into variables. So this is nothing but R of x1 and then x1, right? X2. Like this. Similarly, you can do for any in many variables. In this is nothing but, okay. So so on the one hand, you can write down that polynomial ring over R1 with all those other variable, or you can choose n minus 1 variable and then x. Okay, so now what is the natural question to ask? That what kind of structures it preserves throughout this polynomial ring? For example, you see, if you start with the field f, and if you go to the polynomial ring, then it is no longer a field, right? Then it is Euclidean domain, right? Okay, so it decrease, right? Now if you start with the Euclidean domain and if you go to the polynomial ring, you try to find out what is this kind of structures, whether it's Euclidean domain or not. Okay, and what about principal ideal domain? So for example, if your so do it is actually Euclidean or not, so find out. Okay, the answer is no, this is no longer Euclidean domain. Okay, similarly, if you start with this principal ideal domain P, and you want to find out the polynomial ring, and then you say, oh, you want to say this is PID or not, and the answer is also again no. Okay, find out example here. So find out examples. Okay, example is trivial, you can easily find out. If not, then in the next lecture or next class I will discuss. Okay. So these properties are fails. What is the minimum kind of property which is carried forward throughout the star of polynomial ring? This is very important question, and it was we will prove that it is the properties unique factorization domain that will carry forward. Okay. So to prove these properties, so let me just discuss very important theorem which we call Gauss Lemma, and so let us discuss that. So this is named after German mathematician Carl Friedrich Gauss. Okay, so yeah, what is Gauss Lemma tells you that suppose you start with a unique factorization domain, and then you go to the field of fraction of that unique factorization domain. So let me write down properly. So let R be a unique factorization domain, and A be the field of fractions of R. What does that mean? That means the smallest field containing R. So what does that mean? Whatever non-zero element of F R is there which are not invertible, they become invertible inside F. Okay. So and let you have a polynomial, say P, whatever should I don't Px in the polynomial ring over Rx over R. Okay, so this is that thing. So the Gauss Lemma tells you that that there is a relationship between the factorization of these two polynomial ring. One is the polynomial ring over R, and another is the polynomial ring over F. Okay, what is the relationship? So so this tells you that if you can write down Px equal to some x times Bx in Fx, that means if you can factor into Fx, and then you can do it also inside Rx. Okay. Then you can write down Px as some small x and small bx in Rx. What does that mean? That means if capital Ax and Bx are element of Fx, then you can write down in small x, small b, which is element of Rx. Okay, with what is the property that the small x are actually some multiple of Rx, like some kind of field multiple. Okay, so you can say that is something some constant multiple of capital X and Bx equal to some R2 of where this R1 and R2 are element of the field. This is very important. You can find out the element from field which multiply to give these things. Okay. Yeah, we will show that this you cannot choose this from ring for arbitrary polynomials. Okay. So we try to first understand what is the Gauss Lemma is saying. Gauss Lemma is saying that suppose you have a unique factorization domain which is, I mean, you know that the meaning that you can write it down. Non-zero non-negative element is product of irreducible factors, and this is unique up to associates, right? And then if you go to the field of fraction of that unit factorial domain, and you find out that given a polynomial in original polynomial ring of over R, it becomes reducible over F. Then the original ring is polynomial is also irreducible inside R itself. Okay, and so the proof is not so simple, so we need to try to understand. But but if you do it carefully, then you can find out. Okay, so proof. So you need to understand proper or line by line. So what is given? So it is given that your px equal to sum ax into bx. Okay, in fx. Okay, what does that mean? That means your polynomial ax and bx are element of fx. Okay, so what does that mean? That means so ax are so a is kind of a polynomial in fx, so you can write down some. Okay, so okay, let me write down other way, then it will be difficult, easy. Something I can write down some a0 by b0, a1 by b1 x, and something say okay, maybe I will write a0 dash, that will be easier. A1 dash n by n dash x power n. Okay, similarly b, say these are element of f, right? A0 by a0 dash, and a0 dash a1 dash is element of R. Okay, and also obviously f also, and bx you can write down say b0 by b0 dash plus b1 by b1 dash x, so on, something say bm by bm dash x power m. Okay, this kind of thing. Now see, once you have this kind of expression, then what you can do, you can just multiply by the common denominator. Like if you multiply a0 dash a1 dash n dash by the above thing, then it becomes an element of Rx, right? Similarly this. So what I can say, so we can multiplying throughout the common denominator, like this is product of a0 dash a1 dash n dash b0 dash b1 dash bn dash. So after multiplying by a common denominator, so we can so if you multiply common denominator, so for example say d, suppose this is d is what? This is kind of GCD of, or rather LCM of, you can say that this is kind of LCM of a0 dash a1 dash a1 dash, similarly, and also b0 dash and bm dash. Okay, all those multiplication. In multiple, then what happened? Then so then, I mean, whatever. This is one of the example I'm showing LCM. It can be any multiple. Okay. Then what happened? Then we have d equal to d into your px equal to some new polynomial, right? Fx and e dash x and some b dash x, right? So this is in Rx now. Okay, so this a dash x and b dash x, the element of Rx is okay. Now thing is that so this is not quite proof, because you have a d inside left hand side that we don't require, right? So now we will use something called method. So see, okay, so so we are in a UFD, right? Um, so you can write down d in terms of some, say, d1, d2, and some dk, okay? Be the irreducible, or be the okay, factors factors in irreducible part. So d1 d2 d are irreducible or irreducible element in R, okay, because R is UFD, right? So you can do it. This is given that, okay, so maybe did I write down that thing? R is UFD, okay. So you can do these things, okay. So these DIs are actually irreducible factors, right? And we know that in UFD DIs are also prime, because irreducibles are prime inside UFD, right? So what does that mean? That means, so now I will do something, say, induction on induction on this K, okay. For example, obviously it can be unit also, so maybe I can write down unit times, then write down unit times something, okay. So if K equal to 0, then D is a unit, okay. And then this is obvious, right? Then you choose, if D is a unit, then you can invert both things, right? So you can choose your x, small x, okay. So you can choose your small x is, say, the inverse of a dash x, small x, and bx equal to b dash x, and that is enough, right? Because you use unit, so you inverse a dash x is an element of Rx, right? So they are also element of Rx, and we're done. Now when k equal to 1, then what happen? So this is induction. So if k equal to 0, if you prove, then if you can prove k equal to 1 also, fine. So for k equal to 1, so let me assume that this is true for any k. So let us assume that so what I'm saying that assume that you can write down your a okay, so so yeah, this was the obvious part. Now if assume that that this is true for, what is happening, that the statement or original statement is true for any such any factorization having less number of irreducible factors, okay. So so what does that mean? So I mean, if you have less than k many factors, then it's true. You can write down that thing, product of two polymers inside Rx. Now so you start with, say, D1. So not let, so as D1 is irreducible D1 is also prime, right? In R, and so this ideal generated by D1 is a prime ideal. Right? So you have a usual thing, so it's prime ideals. And what does that mean? So that means prime ideal. So this is not only prime in this, is also prime in, because this is irreducible inside R, right? So it's also irreducible inside Rx, and it's inside Rx also, right? So this is prime ideal in Rx, right? So what does that mean? That means that if you quotient modulo things, so thus the quotient ring that Rx mod this, so this is actually isomorphic to R mod D, I would say D1, and then this, right? So so this ring is an integral domain, right? This is okay because you are quotienting out by a prime ideal, so you will get an integral domain, right? Now if you have an integral domain, then you know that there is no zero divisor, right? So what you can do, you can just go modulo that integral domain, this equation, yeah, so this equation, maybe I can write down star, yeah, okay. So now going modulo D1. So what does that mean? That means you are dividing by D1, you are crossing out doing D1, the star becomes, what the star becomes, so if you go this star becomes what? Star becomes a1x, so a dash x bar, b dash x bar, that will be, see, in the left hand side you have D, right? And you know that inside D you have D1, so if you go modulo D1, that becomes 0, so this becomes 0 in R mod this, okay, which is an integral domain, right? So what does that mean? That means at least one of the factors is 0 modulo D1, okay, so that is at least one of the factor is 0 in R mod D1x, and hence so what does that mean? Hence so either okay, so either this is belongs to this, whatever the ideal generated by this, or b dash x, right? What does that mean? That means either D1 divides all the coefficients of a dash, or D1 divides all the coefficients of A2, right? Sorry, B dash, right? So thus so if D1 divides, then what happens? So thus either D1 divides all the coefficient of a dash x or b dash x, all the coefficients, right? So what does that mean? That means you can cancel out b dash, right? So in the star, so D1 is here in the left hand side, and you know that D1 also sitting inside either A1 dash x or D1 sorry, a dash x or b dash x, so you can cancel out. So what does that mean? That means you can so one can cancel d1 from both sides of star, right? So what does that mean? That means you have a the number of irreducible factors of d become less, right, if you have cancelled out, and then by induction hypothesis you have the same thing. So thus by induction hypothesis we have the result. Right, induction tells you that you can also write it down into small terms, like in product of element from Rx. So this is actually the proof. So so that proofs tells you that the theorem tells you that whenever you have something which is not which is yeah, so 1 minute, so let me check it. Yeah, so I see I'm not writing 2-3 lines here, but this is, I think you can write it down, because after that you will have like d2 d3, right? So this is some dn into px, and then here so after this division, what you can write down, say for example it is divisible, all the coefficients of this divisible by d1, then you can write down d1 into beta x, and note that this is element of this a dash of x of d1 is element of rx, because you can the division is possible, right? Now you do again, the discipline tells you that you can manage all those things, and after managing all those things, whatever you are getting, this will be again element of rx, right? So and now obviously you can just multiply by this d1 d2 d3, and you will get back your p1. And so originally I wrote something, yeah, where is that? Yes, so this r1 r2, then you can come. So what is r1 will be some product of for example r1 would be 1 by say d2 d3 d5, and r2 may be d1 d7 d9, something like that. Okay, 1 by or product of those things. So those will be element of f, and then you are done. Now note that what I said, this is not possible to factor. So you can factor inside Rx, but with the condition that these elements are actually coming from the field f. Okay. So maybe I can give some counter example. So example, and then you will understand. So what is the example? Example is that so suppose we have say px which is equal to something like that, maybe x cube, and then we are in whatever you just in say qx, you have the factor say 5x cube 5x square into 1 by 5 into x. Okay, so this is a factor in qx, right? Now you see that obviously it's reducible, so you can have factors, but there will be no such factors. So you can write down px in terms of ax bx in zx. Zx is the polynomial ring, and this is the unique factorization domain, and this is the field of fractions, right? Give you the field of fraction of z. But here you cannot find any so this is my capital X, this is my capital BX. Okay, so this is my capital X, this is capital BX. Now you see that this if you write down this capital X in terms of sub r1 into x, and you see that this r1 has to be, I mean, you cannot find any r1 with r1 belongs to z, is not possible. So you have to choose r1 equal to 1 by 5. Then you can have fx equal to x square, and this is not all. This cannot be possible, right? So this r1 r2 has to be element of the field. Obviously, for some cases it can be element of it, but in general you cannot say that. Okay, this is very important observation. And one more observation, or rather you can say corollary, you should say that okay, so corollary. But before writing the corollary, let me define some terminology. So definition. So let fx equal to something, say a0 a1 x plus n x0 n element in some polynomial ring. So we define the content of the polynomial fx by, so we write down the c of fx, or sometimes c of x, okay, whatever. This is the GCD of the greatest common divisor of this a0 a1 n, okay. And a polynomial is called primitive, means primitive polynomial if the c of that polynomial is 1. That means the GCD of all those coefficients is 1. Then it's called a primitive polynomial. Now corollary to the above Gauss lemma is very important also. So corollary. So what you can say immediately, so let R be a UFD, okay. So and then you can say that okay, then and then any polynomial Px belongs to Rx is irreducible in Rx if and only if Px is irreducible in Fx and Px is primitive polynomial. Okay, Px is primitive polynomial. So yeah, so this is a direct corollary, and one part is obvious because we just proved that is. So what is fx? Fx is the field of fractions. Okay, so fd and fx field of fraction of R. Okay, so one part obvious. We just proved that if it is reducible in fx, right? So proof. I'm not writing, this is a simple proof, so you can easily prove it. Just let me tell you, if fx is reducible inside if a polynomial px is reducible inside fx, then we know that it is also reducible inside Rx, right? We just prove it. Gauss Lemma tells that thing, right? So what does that mean? That means if it is irreducible inside Rx, it is also irreducible inside fx, right? Now conversely, if it is reducible inside fx, sorry, Rx. So the converse part, let me write down. Conversely, yeah. So irreducible inside of Rx if and only irreducible inside this and this. Okay. So if it is irreducible inside, so if this part reducible inside Rx, so what does that mean? That means if it is reducible inside Rx is also reducible inside Fx. That is from Gauss Lemma. Gauss Lemma tells you that whenever something is factor inside the filter fraction, you have factor inside some. I mean, you can write down this in terms of reducible factor inside Rx, right? So what does that mean? That means if it is irreducible inside Rx. Okay, so let me write them properly. So from Gauss Lemma, what do you have? So if Px is irreducible in Rx, implies Px is irreducible in Fx, and obviously, and see why I'm saying that primitive, because if it is not a primitive, then the coefficient will be something element of R, and then it is no longer irreducible, right? And Px is primitive. Okay, conversely, if Px equal to Ax Bx reducible in Rx, then this is also inside, this is also in Fx, right? So thus also reducible in Fx, right? So this is the proof. So what does that mean? That means if it is irreducible in Fx, then it's irreducible in Rx. Okay, done. So this is the proof. Yeah, I think maybe I should stop here. Okay.